I thank the organizers for giving me an opportunity to share some of my points on applications of numerical methods in fluid mechanics. So before starting the applications, I just want to wind what is the existing availability and how we can still improve it. As we know very well that any of the engineering or any problem that exists should be reduced in the form of differential equations. So the motto is to solve the differential equations. But to our knowledge, everybody knows that the limitations of mathematics, even we cannot solve second order quadratic linear algebraic equation. So, but in order to define even a single pen or a single point, we need 3 dimension. But exact solutions are not sufficient for us to define even a point that exists in reality. So, what are the other possibilities? The other possibilities is we switch on for approximate solutions. However, in analytical methods, apart from the classical method, like taking a differential equation, writing its algebraic equation, finding the roots, and then depending on the nature of the roots, we write the solutions. That is the classical method. In spite of that, I don't say that mathematics has stopped there itself, but many of the researchers found some of the analytical solutions also, but under some restrictions. Suppose my differential equation is like Bessel's function, hypergeometric function, then some special functions, there we can get some of the exact solutions. But it's not possible to find the general solution for even simple second order ordinary differential equations. So researchers thought, why not we go for other methods like approximate solutions. So here my point of view to highlight these points is exactness is always better than the approximation. So for all the researchers, what I wanted to suggest is whatever you have your differential equation at hand, first search for all possible exact solutions. If it is not at all available, if it is not at all possible to find the exact solutions, then only switch over to numerical solutions. Next, what are the numerical solutions that we know till today? I just give a brief introduction about the numerical methods. So, traditional numerical computing methods, even before the computer era started, even with the help of what we say calculator, we used to work with numerical methods, simple numerical methods. Normally, we bifurcate finding the roots of the equation is as good as, as I already told, finding the roots of the equation is as good as finding the roots of the differential equations. So we must know what are the roots of the algebraic equations. In numerical methods, we have bisection, Regla-Falsi, Newton-Raphson, secant methods. And solving system of algebraic equations, we go for Gauss elimination, Gauss-Jordan, Gauss-Jordan. Also, we have interpolation and regression analysis, such as Lagrange, spline, least square, regression methods. We also have numerical integration, such as trapezoidal, Simpson's, Romberg, Gaussian. Differentiation. For differentiation, we have all these methods we study in master's degree. Some of the methods we also study in bachelor's degree. And going for solution of differential equations, the well-known Runge-Kutta method. Even we use Adams-Bashforth-Moulton method. And for boundary value problems, we use the shooting method, finite difference, power method. And the set of algebraic equations, when you go for numerical methods, especially finite difference or finite element methods, we get a set of matrix of order n cross n. So solving the matrix of order n cross n itself is a challenging when we go for numerical methods. So we must satisfy, if I want to apply, say for example, Gauss elimination method, I must be confident that my matrix has diagonal dominance. There are many methods that you need to cross check before you apply solving the system of algebraic equations. So there are many hurdles in handling the numerical methods also, but we have to find some approximate solutions when we don't have any solutions at hand. Here, we know very well that Newton-Raphson method, the formula we apply is xn equals to xn minus 1 minus f of xn minus 1 divided by f dash of xn minus 1. Whenever we use any of the numerical codes, normally we tell that this code is good in terms of its accuracy, less error, and it should consume less time for computation, because after all, power is money. So a good programmer is a one who gives the best program in terms of its computational time, its convergency, order of accuracy, and the percentage of error. So when we are using these numerical methods, it is well known that instead of considering the derivative function, if we consider the point difference, f dash is what? F dash is nothing but the difference between two intervals under the assumption that h should tend to 0. H should tend to 0 in the sense that the interval length should be small. So as you go on dividing more number of intervals, naturally the computation time will be more. So what the improvement can be done, instead of using the derivative function f dash, we can replace the derivative function by its intervals. Suppose if I remove limit h tends to 0, that means I replace f dash of xn minus 1 in terms of its ordinates. That means here f dash of x is not depending on limit h tends to 0, but it merely depends only on x and x plus f of x. So this is what the researchers tried, and these methods we call it as Stephenson type methods. So in order to have a good program, you can improve the Newton-Raphson method. Instead of using the classical formula, we can replace the derivatives by the ordinates. So with this, we can proceed that not only Newton-Raphson method, we can also apply this technique wherever you have the numerical formulas wherein you are using differentiation, we can replace by their ordinates. So this is what I just wanted to highlight. Don't depend on the classical methods, but identify in the literature what are the improvements that can be done. So this is one example I am giving for you. So replace the Newton-Raphson formula by modified Stephenson formula. That gives you less time, more accuracy. Then similarly, we can use even for 2 steps. These are the modified Stephenson formulas. Similarly, Chebyshev, then modified Chebyshev. It's only we are replacing, instead of derivatives, we have the ordinates. So this is the beautiful technique that the new research scholars can use these modified formulas to improve their programs. Hello, you will find in any of the textbooks all these things. I just wanted to locate that instead of using the derivatives, there are possibilities that you can replace the derivatives by their ordinates. So this is one of the method. Next, we'll understand in totality what are the present numerical methodologies we have. We bifurcate them into 3 forms. One is finite difference, another one is finite element, and the third one is spectral method. So the researchers should understand for what type of problem we have to apply which method. When you are having finite difference method, the word finite difference itself will tell that the domain of your study, the geometry under consideration, you must have the boundaries, fixed boundaries, not irregular boundaries. You must and should have regular boundaries. Say, for example, square, or you should have a well-defined tube or circle, like that. Well-defined, that means your domain of definition should have fixed boundaries. In that purpose, you can use finite difference method. Then, when to use finite element method? This can be applied, you can apply even for regular geometry and also for irregular geometry. Irregular geometry in the sense whenever you don't have good topological space. So in that case, irregular boundaries, you can use finite element method. What is the drawback when you are using finite element method? When we are using finite element method, the drawback is, I don't have a pen. Just imagine that you have an irregular boundary. So irregular boundary, when I am here in finite difference, I chop the interval. Whereas in finite element, the word element itself will tell that I divide my whole space into small elements, integrate each element, then get the solution. So what I am going to do is I am taking complete volume space here. So when I am taking complete volume, either I divide it into a triangular mesh or a square mesh. Nowadays, recently, Kelvin cells, people are also going for the chopping of your irregular boundary with Kelvin cell. I reviewed one paper published in IJHMT. It's the first paper that I have seen in the literature that apart from our regular triangular or square finite element method, they have used the Kelvin cells. So everybody should read that paper. Last year only it got published. The authors are Oranzia Manca and Bernardo, and from Turkey, one more fellow is there, Safa. IJHMT 2023, it got published. You must and should read that paper. So, but when I am cutting my irregular geometry into regular geometry, there is an error because either I take extra space or I leave some space. So error is bound to happen even when you go for finite element method. What are spectral method? In finite difference method, we can go for point-wise. Again, in finite difference method, if the coordinates, if it is one-dimensional, okay, no problem. If it is two-dimensional, again, the complexity increases. Because if it is one-dimensional, I get a very beautiful matrix. I can use Gauss elimination and then I can solve it. Suppose if I have two-dimensional, how I have to move from one step to other step? I have to first complete the level at x equals to 0, get those approximate solutions, then go to y equals to 1, complete all the grades, and then, so it is a very tedious process when you go for one dimension to higher dimensions. So finite difference method, but whereas in finite element, that problem is not there because we are completely taking full volume. So after knowing this volume, we go next volume, next volume, next volume. So number of volumes we directly, and then we add them and then get the solution. Whereas in there is no difficulty when you go for uh, what I can say, ordinates. Ordinates in the sense it is dimension. In finite element, if you have one dimension, two dimension, three dimension, is not a big deal. But when you go for finite difference, the program and the programmer finds very difficult and it is very tedious also. So these are the loconos that we come across when we use finite difference, finite element methods. And of course, the spectral method, normally we don't see when you observe in the literature, most of the people, they have used finite difference method, especially for fluid mechanics problems I'm speaking. Finite element methods, physicists are using finite element methods. But whereas for fluid mechanical problems like Blotner method, Keller-Box method, these are all depending on finite difference method. Recently, finite element method people are trying, but it is not again a easy task. In order to solve one-dimensional problem only, when you do finite element method, it takes lot of time for the computation purpose, because it depends on the size of your volume. So when you go for small volumes, accuracy will be more. So there are a lot of difficulties while applying even finite element. So normally finite difference, like we have in fluid mechanical, we take a flow through channel, flow through tube, flow through circular pipe. Geometry is fixed. So we find in the literature, before 1960s, before the era of computer, uh, the people tried to use these good old methods, even Rangyakutta method as such. But we don't find a lot of finite element methods used in fluid mechanical problems. So, next, these are the tips that I am just going to share with the researchers, that how to handle the numerical techniques. So, preliminary computational techniques. So, what are the post processing, pre processing, and what you must have before going to paper? What are the things that you should think over? So, I just take fluid mechanical problems only. So, when it is a fluid mechanical problems, we come across velocity, pressure. After all, Navier-Stokes equation is a balance between F equals to ma, that is total forces acting on the body must be equals to mass into acceleration. So it deals with only the forces and acceleration. So the parameters that we are bound to find is nothing but your velocity, if it is 3D, UVW, and pressure in the absence of gravity. So a simple method. So how we have to, these are my unknown solutions. So for three-dimensional, what you have to do is take the governing PDEs along with your boundary conditions. Governing PDEs are nothing but my Navier-Stokes equation. Do the discretization, you get system of algebraic equations. Use any of the equation solvers like Gauss elimination, as I have already told, Gauss Jordan. Use any of the equation solver methods. Then you get an approximate solution. So here also, when we are going from in order to find out the solution at n plus 1 step, I need to know what are the solutions at nth step. So one should be wise enough to suppose if I have x equals to 0, x plus h. If I take interval 1, then it will be uh, x1, x2 at the nodal points. So in order to evaluate x3, I need to know x2. In order to evaluate x1, I need to know x0. What is x0? Is nothing but my boundary condition. So boundary conditions play a vital role whenever you go for numerical method. So one should be very good enough in handling the boundary conditions. The two, if you are having boundary conditions independent, like constants, it is easy. Again, suppose if your boundary conditions are depending, it's difficult to handle. Of course, here in that case, one should be wise enough in judging what should be the initial solution. If it is fixed boundary, if it is constant, yes, that will take care. But suppose if it is like, suppose if I am using boundary conditions of third kind, in that case the solutions depend on the variables, depending variables. In that case, one should be wise enough to judge by, this comes by what I can say, experience. So this is the standard method. Once you get approximate solutions, you can improve it by computation, n plus 1, n plus 2. That's what. The accuracy depends on how small you take h. How small you take h, that will be, but taking small h improves your matrix, takes lot of time for computation. My own problems I cannot solve in my laptop I cannot solve it. So simple one dimensional problem I could not solve it. There are many challenges even in numerical methods also, but human tendency is to try. So numerical methods, you should have a good judgment, and also you should have some knowledge about its physics, some knowledge how the profiles look like. You must have some good basic knowledge about your research problem. That is very much essential. These things are not necessary when you go for exact solutions. So that's why I suggest try. If your basic equations match any of your existing exact solutions, be happy. Otherwise, numerical, it has its own limitations, but something you can come out. And the only validity is nothing but we have to validate, because whenever you run anything in the program, in the computer, it gives you the answer. But who has to judge whether that result is correct or not? There is a saying, garbage in equals to garbage out. So what we put in is equals to what it comes out. But putting in how best we are correct. Who has to judge? So normally in any of the numerical fluid mechanical problems, the general procedure is what we will do is we just validate our results with already published papers. That's all. We have some kind of fluid mechanical aspects. So, for example, if Grashof number increases, naturally flow increases. I should get that result. Like something like, I don't know if I don't get. Maybe your equations are correct. Your program is also good, but my classical result is as Grashof number increases, buoyancy increases, therefore velocity. Yeah, heat increases, therefore velocity increases. But if that doesn't happen, you are correct, your equations are correct, your program is correct, but it is not satisfying your classical results. So these are lot of complications are there when you are going for numerical methods. But we have to try. So who knows, my equation will get run and it satisfies all the physical properties. Be happy, that's all. Then the paper will be published. That's all. Okay. So now what are the conceptual implementation? So first, set up the grid. As I already told, what you do is in order to run your program, you take less number of grids. Program should run because there are depends on the capacity of your laptop, its memory, its RAM. The computer will hang. Suppose initially itself you give large number of grid. So go systematically step by step. Then what you do? Initialize dependent variables. That's what I told. Initializing dependent variables is the smartness of the researcher. If your boundary conditions are constant, nothing to worry. But if they are not constant, you should be wise enough to guess your initialization. Then construct finite difference analog, PDEs and B boundary conditions. For each interior grid, TJ, evaluate n plus 1. So knowing n, evaluate n plus 1. So how to stop it? As long as the error between n plus 1 and n step is less than your required accuracy. Your required accuracy, again, it depends on your research problem, whether it should be 10 raised minus 6 or 10 raised minus 8. Again, on your capacity of your computer, there are so many inbuilt programs to judge the accuracy. So if it is yes, stop. If not, repeat the process. This is the normal thing. Now, here I want to highlight one very important thing, that whenever you have unsteady problems, so unsteady means one more dimension is increased. So whenever you are using numerical methods, if dimension is increased, it becomes very difficult. So how to reduce the dimension? With respect to time. So what we are going to do is, I will write my Navier-Stokes equation without my time bound. I don't consider, that means reduce the equations for steady case. Then what you do is write your program. Then I have to know the impact of time bound also. So dou u by dou t. So it's a first order derivative. So dou u by dou t means I need, when I put it in finite difference. So with respect to time bound, what I will do is initially I take time equals to t equals to 0, run the code. Then repeat the same code for t equals to t plus delta t. Delta t is say 0.5 seconds. You get solutions. So that this will give you a very beautiful handling of reducing one dimension. So these things are not explained in any of the textbooks. That's why I'm more specific on time bound. This is the best method. So of course, directly you can solve when you are having unsteady problem, but it's very difficult. The program, writing program, because each step you have to go in Crank-Nicholson. If I take even for one dimension unsteady, you are seeing in Crank-Nicholson method, one dimension unsteady also, I have to finish time t equals to 0. Then lift to time t equals to 0.5. Then lift to t equals to 1. Instead of going in the program, it is better you run the program for steady case and then give increment. Here I have written. Repeat the steps tn plus 1 equals to tn plus delta t. So you get I mean, it takes computational time is also less. You need not scratch too much your head for writing the program from one level to other level. So these are the, now we go for what are the existing softwares and how easy. When I was doing my research work way back in 80s, I mean, end of 1990s, like 1986, 87, 88. That time we didn't had even what I can say, computer where we can use our input data to draw graphs. Even to cite one paper, we used to go to library, get Xerox, get it done. Lot of difficulties. So those were the time we did research work, drawing our results on the trace sheet and then post it to the editor. Then they used to take the photo print and then print the papers. Those days are gone now. I just wanted to highlight how fast the technology has developed. So we have lot of softwares now. For example, MATLAB. You just imagine, suppose j equals to minus d into dc by dx. It's a one dimensional and I can get happily exact solution. Instead of that, if I include unsteady term, dou c by dou t equals to minus dou d dou square. Mathematicians know how difficult to solve this equation. Of course, we can solve it. Honestly telling, I can tell that we can solve it. It's similar to heat equation, but how much difficult it is. When we use MATLAB, just some 5-6 statements are enough. 5-6 statements are enough. So fast the technology is. No need to worry. So just I'm giving you the glimpses, the importance of the softwares, using the softwares like MATLAB. MATLAB itself will tell it is for mathematics. So one should cope up. The youngsters should cope up with the recent softwares, MATLAB. Now you can see, in order to get this plot mathematically, how difficult it is. How difficult it is. But with only 3 statements, we can get this. This is nothing but plots of Mercury orbit around the sun, using only these 3 statements. So it's very handy. It's very handy. Now I just want to give you the overall picture of what are the existing softwares. I restrict myself for fluid mechanical problems. What are the commercial codes that we use? As I have already told, MATLAB. You have ANSYS Fluent. In ANSYS Fluent, we use finite element method. So Adina, FSI, COMSOL, even in COMSOL also finite element method. Specifically, I am mentioning it. FreeFEM, and then Mathematica, and then Maple. Of course, Mathematica, Maple, and MATLAB, we can handle one-dimensional or two-dimensional ODEs, but The standard methods for PDEs are ANSYS Fluent and COMSOL. Even FreeFM++ is also okay for handling the actual fluid mechanical problems. So in finite difference methods, we have Keller, Nakamura, Leapfrog, Dufort, Frankel, Blotner. These are all inbuilt programs. Just you can take this program, fit in your equations. You need not worry for writing these codes. They are already inbuilt. Just take the code, fit in your equations. You can run your program, get happy, no problem. And regarding its stability, regarding its accuracy, everything is taken care by these methods. Then we have not only numerical and analytical, we have recently, I think some 20-25 years, we are finding some semi-numerical methods like homotopy method, and then even Keller box comes in here. What is semi-numerical means? What we are, if even I'm using, what is that? Using Taylor's expansion, finite difference. You can Google my account, you will see. Long back I used in some 6-7 years, but it's a good method. But there also I found some technical problems. I could not, because Taylor's is for you get x squared h. So some problem I could not handle it. What the method is, DTM, differential transform method. Why it is called semi-numerical? Because initially I used Taylor's expansion. From the Taylor's expansion, I take my basic equations and use the algorithm. So that's why it is called semi-numerical. Then we have variational methods, spectra, finite, FINTTF. Here I have mentioned 1D, 2D, 3D, excellent commercial codes, but of course you need to pay a lot for ANSYS Fluent. Individual purchasing may be costly. Of course, you should take the help of the organization, purchase it, and then you can use it. I use ANSYS Fluent and also COMSOL. Okay. Now this is a bird view of how to handle the fluid mechanical problems. Now I go in particular one application. The recent well-known CFD simulation of Magellan bullet train aerodynamics. How ANSYS Fluent helps us to calculate the speed of the bullet train. So here you can just visualize. It's only a visualization of different models of bullet trains. I want to specify, you just observe how the geometry looks like. What is this geometry? What is this one? And what is this geometry? The nose and the tail of the train. So first of all, what is Maglev propulsion? I'll not go in detail. Everybody knows it. So earlier, which technology is used, and now which technology is used for. It's all about your magnetic, the strength between the magnets. So in order to understand in detail, you just Google it, you will understand. So Maglev propulsions, here I have given the advantages and disadvantages. I'm not going in detail because I need to complete. Here, the first Maglev train, Shanghai. It was launched in Shanghai in 2002 itself. In 2002, it was operational, but research started in 1991 in Birmingham Airport. It covered 30.5 kilometers for 431 kilometers per hour. They launched in railway station to Shanghai International Airport. This is the first launching of bullet train. Now you can see how is the shape of the bullet train. It is little bit like aerodynamical. It is not straight. It is not straight in the bottom, and it goes like aerodynamical property. So there are no any blunt edges. You don't see any blunt edges because here whenever you have a flow, how easily it flows when you don't find any obstacles. But space, we are in space, so we have obstacles. What are the obstacles that we are facing? If the pressure is less, the flow is fast. If the opposing force in terms of anything, it may be air or it may be dust, or it all depends on the geography of where you are launching your train. So as long as you have less opposing force, flow will be fast. So here, in order to have the flow smooth, so what opposing force should not hit your object. It should pass your object. So in order to pass your object, how should be the geometry? So in order to pass, if it is a straight line, it will hit and it will not pass. It will directly hit. So in order to pass it, we have to make it aerodynamical. So blunt edges are not suitable in order to get a high flow. Therefore, next we have superconducting Maglev trains. In the superconducting Maglev trains, you see the nose of the train. Here, as I have pointed out, the pressure should easily pass. It should not create lot of force on the object. So, what they did is they changed the nose in the form of the shape of the duck. We see duck, no? Of course, research is now depending on what is existing in nature. We are mimicking the nature. We are mimicking the nature. Recent researchers, we are mimicking the nature and we are developing our technology. It is nothing but it shows the nose of a duck. So here, sorry for the interruption. So we call this as L0 series. It was launched in 2015, but the speed is 603 when compared to 415. This was launched by Japanese people. Now, I just give you the glimpses. This is the first one, Transrapid. Here, you can see the shape. First launched Maglev train. Then here you can see it is aerodynamical. In the third one, we can see that not only the nose, but even the tail is also aerodynamical. Tail also aerodynamical. Not only the aerodynamical property, the flow will be fast even if you consider the thickness of the object. So they have reduced the thickness of the object. So at present you have Transrapid 09. And here, this is the super bullet Maglev train. The dream of Chinese people is that they wanted to create a Maglev train equal to the speed of the aeroplane. That is their dream. So is now a world leader in developing Maglev technology. So they wanted to reach the speed of aeroplanes. Whatever the speed is there in the sky, they wanted to put it on the road. Next, we have used CFD and ANSYS Fluent to model the Maglev train technology. So define the goals, identify, then create the geometry, create the mesh, define its physics, and then solver setting. Because of timeless, I'll go for displaying my results. Here is the geometry, train 1, blunt in the front and nose. Whereas in train 2, it is blunt in the nose and here train 3. So these are the results that we have obtained. And we have taken the help from NASA. And we have modulated theoretically using ANSYS Fluent bullet train of speed 900 kilometers per hour. So this can be done using ANSYS Fluent. So design 5 was used as it performed slightly better at the speed of 500 and 900 kilometers per hour. So we can now give you the values. With what geometry we can successfully get 900 kilometers per hour. So this is the geometry created in ANSYS Fluent. So further, what research can be done is develop the model in 3D, use varying lengths for the train body. So thickness also counts a lot, and including the length of the body also. Testing models in a wind tunnel to compare simulations to their theoretical results. Then simulating the deformation of train material and properties. Modify the model to incorporate full McLeod train body and track. Use much faster hardware. That is the challenging problem. Whenever you use ANSYS Fluent for complicated geometry, you cannot use it for using your any highly sophisticated laptop. You have to have uh, some organization link, then only you can run such big programs. So denser meshes, here for this one 10 million elements are used. As I told ANSYS Fluent, we use a finite element method. So for this geometry, it is being used 10 million elements. So so it can be improved. Still you can improve this design and conclude for what type of length, what type of thickness, what type of aerodynamical properties, you can get the best model. So actually, I have published one of my paper in IJHMT, how to handle finite difference method, especially for young researchers. I wanted to explain how to handle the boundary conditions and interfacial conditions. Because of no time, I need to wind up. But however, I will give you the reference. I published in IJHMT and also in Journal of Magnetism and Magnetic Materials, interfacial problems. So you can refer just Umavathi. So